So welcome everyone. So my name is Colin Barre-Brisebois, and I'm a rendering programmer at EA working on Frostbite 2 and Battlefield 3. And today, Marc Bouchard and I would like to present to you a rendering technique which we have in Frostbite 2, which allows us to approximate translucency for just like the title, a fast, cheap, and convincing subsurface scattering look. So, just like the title says, basically this technique will allow you to add convincing subsurface scattering-like translucency to your scenes at a very reasonable cost. So, let's begin. All right, so here's the agenda for this talk. So in order to really show what the talk is all about, we begin by demonstrating the technique with a video capture of the effect implemented in Frostbite 2 engine. And once that's done, we'll revisit translucency briefly, the current state in the games industry, how our technique differentiates itself from previous implementations. And then we'll be able to go in the full details on the mathematics behind how we get this, how this works basically, so that it's easier for you to implement this in your next game. So let's begin by the demo. So overall, the capacity to simulate translucency in real time can have a drastic impact on the art direction. I mean, I don't have to convince you when I say that, like post-processing allowed post-frame visual treatment to a rendered scene. Translucency can definitely, have a drastic influence on the visuals. And the main reason behind this is because translucency, allows us to add a new volumetric dimension to the scene. I mean, we're not limited by opaque or semi-transparent polygons anymore. And this basically allows us to describe how surfaces are made, but from the inside. And I mean, of course, we know that, our world is still made of polygons, but if we combine intelligent visual trickery and light camera and clever shading, we can make it so as if those objects are not hollow at all anymore and actually translucent. So let's quickly review and discuss the current state of translucency in computer graphics. So, first and foremost, I guess one could summarize translucency by saying that it's the quality of allowing light to pass partially and diffusely inside media. This applies to non-organics, such as the statue of Athena here, made of like PVC plastic type, and organic surfaces, such as Mark's baby's hand to the right. So, in regards to real-time computer graphics, on a daily basis, we rely on mathematical models to reproduce in our games the visuals we find in nature. Most of these mathematical models deriving from theory of light transport are very useful because they allow us to effectively simplify and represent visuals we find in nature, but in real time. So, for example, the interaction of light and matter, we often reduce that to BRDFs. BRDFs are really good for representing, the reflection at the surface of opaque objects, but this is not sufficient for modeling and representing light transport happening inside objects. So this is why we have more complex models like BSS RDFs. But unfortunately, these new models, in order to simulate them in real time, you need a significant investment in resources and, in regards to performance and computation or memory. So our technique here tries to blend or get some elements from both, so the fast BRDFs and some elements of BSS RDF. Also, translucency and derivatives currently present in various game titles, and other real-time simulations. On the more complex hemisphere, you have those SIGGRAPH real-time implementations that are available, but are usually not fast enough for, a game context where CPU and GPU is really busy already at work, so I don't have to convince you, I'm sure. So, we find several convincing versions of real-time subsurface scattering translucency for skin shading, especially in games where you have, permanent characters. And most of these algorithms, exposed from Hable or Chang, they focus on texture space operations for describing the interaction of light with the surface. Either for skin, subderma, light absorption, diffusion, or the popular CG materials such as marble and other surfaces. And alternatively, some people came up with depth map-based versions for calculating the thickness of objects. So this is mostly inspired by Karsten Duxbacher's work, and also you can see this in Key's work. So that's another way of computing translucency. But on the simpler side now, we have games like Crisis, and this is pretty funny when you say, on the simpler side, Crisis. But they have used double-sided lighting efficiently with a gradient mask texture to draw the tree leaves with varying translucency. You can read this in GPU Gems 3, if I recall correctly. But, this solution is very convincing for rendering tree leaves, but it's not sufficient in the case where one wants to render objects of thick volume. So this is where our technique kind of comes in and tries to fill the gap. It has to be efficient like the technique from Crisis, but at the same time get as visually close as possible as the previous ones I just mentioned. So this is what we got. So on the left, we have a scene with 3 lights running in Frostbite 2, which uses Frostbite 2's deferred shading engine, all of which use our real-time translucency technique combined with real-time AO and real-time global illumination. So if you look on the right, but on the left as well, you can see a cube that reacts a bit differently from the other cubes. So basically the light inside the convex hull is green, but the surface emits a kind of red veiny color instead of the expected green. So this information, which I'll describe really soon, is kind of provided on a per material basis and allows artists to author subsurface scattering-like results with ease. So this additional information basically allows us to describe how a surface would react if light traveled inside or through the hull. So here's another example on the left with 2 hands with our skin shading and real-time translucency. And additionally to the right, well, we have the Hebe, which everyone uses because she's cool. But she's very useful for representing stone-like surfaces like marble and such. So now that we've introduced the technique briefly, let's spend a bit of time on how we do this actually, so the technical details. So again, we don't want to rely on additional, and this is really key, we don't want to rely on additional depth maps and texture space blurs for simulating translucency. I mean, while the previously mentioned techniques, provide significant results, they require additional and sometimes a very significant amount of computation and memory, which we don't necessarily have for our, already busy CPUs and GPUs. And moreover, with the current state of computer graphics, several simple elements can be combined together in order to convince the user that, the objects in the world are actually translucent. So first, one of these elements is that the light traveling inside the shape has to be influenced by the varying thickness of the object. And it also has to show some kind of view and light-dependent attenuation. So basically, if you combine these 2 elements together, most users, will be convinced that objects are actually translucent, but they're not. So also, if the effect is pretty cheap, well, I guess you can justify using it pretty much everywhere. Whereas, the most complex subsurface scattering like translucency techniques, are usually limited to, in-game cutscenes or, very limited moments of your game. So to achieve the previously mentioned, first we begin by using the distance attenuated regularly diffuse lighting, like you can see on the right, but we combine this with a distance attenuated dot product of the view vector and the inverted light vector you can see there. So this basically allows us to simulate basic light transport inside an object for simple shapes, such as cubes, spheres, and stuff like that, because it basically takes advantage of, the dot product in this computation basically takes advantage of the property of radial diffusion of light, But the problem is that it doesn't take thickness into account. So it's really necessary to be aware of this thickness, so that you get a really nice result. And again, we don't want to rely on depth maps for computing this thickness. Depth maps are really cool because they allow you to define a referential, I mean, if you render from the light, you have a referential there, you're looking at that pixel, you have a referential there, you can calculate this distance. But then again, we don't want to add any, expensive or additional computations. We want to do the best we can with what we have. So instead, what we do is we pre-compute in a map that basically defines local variation of thickness on an object. So in parallel, in Crisis, the foliage technique I just mentioned, it's possible for artists to actually paint in a texture where on a leaf, the inner branches on the leaf are. But this is very cool, but unfortunately, this works well for semi-flat objects, and in the case where you have complex objects like this, well, it's kind of hard to, manually paint this. So to streamline this, what we do is and this is the trick, we rely on a normal inverted computation of ambient occlusion, which, can be done offline using your favorite modeling or rendering software. And you can store this in a texture. And since ambient occlusion basically determines how much environmental light arrives at a surface point, we use this information for the inside of the object by flipping the normals, and this basically averages all light transport happening inside the shape. So this is the map we get for our Hebe statue. You can see how it varies around the head, the arms, etc. So to summarize, inverting the surface normal during the AO computation approximate how much light how much light traveling inside the homogeneous media would get occluded at the point where it exits the shape. So this is basically, actually, you can store this in vertex color if tessellation allows. And this allows us to streamline this process for all sorts of meshes. So here's the thickness map for our Hebe statue. So while our technique, is far from being mathematically correct in terms of approximating subsurface scattering, and this is why I mentioned this, what about subsurface scattering? Well, we still get a nice light transfer effect because our local thickness texture is not limited to grayscale values like we saw for the previous statue. You can actually color this. So basically, this color that you can add or, parameterize in that texture basically allows us to add or to get even more interesting results because it basically represents the color that the surface emits, though pre-computed, through the scattering of light. So this basically means that if we know roughly what color our surface would get through subsurface scattering, we can just store this in a texture. And again, this is not mathematically correct and technically far from what has been achieved in Able and other types of papers like that. But at the end of the day, if we manage to make believe that surface has subsurface scattering, well, then we have succeeded. So let's go into some implementation details. So here's a quick overview of the final light transport code we have in HLSL. And this is pretty simple, right? So here what we do is we combine the local thickness with the lighting vectors that you can see on the image to the right. Also, just to give you a quick performance overview, this code only generates about 13 to 15 ALUs based on the platform. It runs on SM 2.0, which nobody talks about anymore, and also on semi-fixed pipeline systems such as the Wii. So again, we have several parameters to manage in order to get this to happen. So at runtime, some parameters will have to be defined per light, and some parameters will have to be defined per material. Obviously, our per light parameters are pushed in the light pass and defined per light, and our per materials are stored in the G-buffer in the case of frostbite. So knowing the G-buffer is space limited, you can also store these parameters in a separate buffer if translucency is really important for you. But also, some parameters make much more sense per material, and some make more sense per light. Actually, most of these parameters I'm going to introduce now make more sense per material, and actually one of them should be per light. So, and I mean, you can shuffle these around based on how your G-buffer is busy, and if you need to save space, there's definitely some packing and unpacking that can be done, and I'll try to discuss that a bit later if I have time. So first, we have an ambient term. which basically describes translucency visible from all angles at all times. So this term basically represents a minimum value of how much translucent surfaces, let light go through. Both visible if the surface is in front, if the light is in front of the surface or in the back. As a second parameter, we have a power attenuation, which basically we use for the view-oriented back translucency, so when the light is behind the object. And, while we usually want view-independent effects, this power is very useful because it breaks continuity in a view-dependent way, which, allows us to get even more interesting and organic results. So, and also as a quick note, you can kind of get rid of this scary power function with some pre-computed powers, basically. As a third parameter, we have a distortion value, which I really like a lot, which is super simple. It basically shifts the inverted light vector based on surface normal and a certain amount. So this factor will basically simulate subsurface light transport distortion happening inside the surface and improve the results and make it even more organic and almost Fresnel-like at times. So to the left on the image we have no distortion, and to the right we have a small distortion of 0.2, but you can definitely see the differences on the nose and on the forehead. So that's for this parameter. Also, our light transport is modulated by the local thickness texture, which I previously mentioned, both for the front and the ambient translucency. So again, this texture basically attenuates the results where the object is generally thicker. And finally, we have a scale value for direct translucency. So this basically defines how much a light will generate translucency when it is behind an object. And basically, that's about the only parameter you want to have per light, and the other one's per material. And this is really important because artists can define sets of materials that they will reuse later. So for example, they can define like plastic or marble and concrete and reuse those fixed parameters on all surface types and basically just have, for the lighting, just have to tweak one scale per light. And this is why this is really important. So if we put it all together, here's our final result of direct, so front and back translucency, and ambient translucency. You can notice how the translucency varies based on the where it is on the head, basically, and how it distorts around the contours of the shape, the nose and the head, and how it's very prominent on the nose. So on the engine side of things, again, I mentioned that we store this in the G-buffer as a single grayscale value. So here's our G-buffer set, one of our G-buffer setups for Frostbite 2. And in the case where, again, your G-buffer is really busy and full, you can store this as a single grayscale value, which I show here on G-buffer 2 and the B8 column. Also, we filter by material ID that you can see just on the right of that. So basically, we can reuse that channel for any other parameter that we like. So here's another example that we have with 3 lights where the objects are basically showing translucency, but only with a grayscale local thickness texture. Now, if grayscale local thickness is not enough for you, like I mentioned earlier, we can store this as a color. And I recommend, taking the grayscale version and playing with it before moving on to the color version, because it has some implications in the case your G-buffer is already full. So since we only have one channel left, we decided to reuse some of the G-buffer 2 channels in order to pack this all together and for it to be available for the light pass. So basically what we do is, and this is a neat trick, so I mentioned we filter by material ID, and our translucency material ID is the last one in the list. So basically what we do is we add the blue channel to that ID, and basically if that value, when we sample the G-buffer for that channel, if that value is bigger than the last ID, well, obviously we know it's translucency, and obviously this is the content of that color texture. Now, we don't have that many material IDs, so it's not too bad. We lose not that much. And we could, scale and shift to get the results back. So we'll never have a pure 0, in regards to a blue channel translucency. But this doesn't really matter that much, and obviously blue is less noticeable than red and green. And I mean, we didn't have any issues with that. In regards to the red channel, there were the local environment maps IDs, which we didn't really care for those objects anyway. So I think that's about it for this slide. Yes, another thing though is that, like I mentioned earlier, you might want to pack things differently in your gbuffer. So what we do, we have another setup where we don't give full 8-bit precision per channel. We give, like, for say 565, and we use the remaining bits to pack additional parameters in the gbuffer, like the previous ones I mentioned. So that's another way to, get things together for the lighting pass. So to the left, basically what you see is a green light with white albedo, but with red translucency. And this is where, you can kind of see the difference from the one to the right, which is just a white albedo and translucency with a blue light. So in regards to performance, well, our implementation on PS3 basically takes advantage of our light tile renderer on SPUs, and I don't know if you saw Christina Coffin's talk, but if you haven't, you should definitely check out the content from the GDC Vault, and also be published on the DICE website. So again, we basically divide the screen in multiple tiles, and we render translucency only on the tiles on the screen that have that material. And this is very efficient in regards to the PS3. So again, you should look at Christina Coffin's talk for more info about this. In regards to our DirectX 11 implementation, it also takes advantage of our compute shader solution. So basically, we can, again, define which tiles have translucency or not. And for more details about our DirectX 11 implementation, you should check out Johan Anderson's talk. And overall, these numbers illustrate that our technique, approximate convincing real-time translucency at a very reasonable cost. This method basically provides significant benefits in the case where developers want a quick impression of subsurface scattering. And again, looking at the instruction count, 12, 13, 17, that's not very much. And it runs on SM 2.0 and as well as on our non-Frostbite 2 implementations. So due to the fact that this technique is an approximation, there's definitely some caveats. And it takes into account the radial property of lights. Some instances will not yield, optimal results, obviously. So the figure here demonstrates one of these examples where the light traveling in and out of a concave, hull at point A and exits and casts a shadow on B. That's not very optimal for a technique. So, while it's possible to generate local thickness that is aware of concavity by changing parameters when you generate that ambient occlusion, it has to be minimized because basically you're kind of losing the values. I mean, if you start playing with it, you'll really see what I mean. But basically, we can't play with those parameters too much and, capture a concave surface. So basically, it works much better for convex hulls. And also, this technique doesn't work with morphing objects. So as an alternative, you could compute a view-oriented screen space thickness that Christopher Oates has demonstrated in a previous paper, but this will basically work only if the light is somewhat behind you in the screen. So, additionally, one could use some kind of hybrid real-time AO technique, but it's getting too complicated from what it really is. So, overall, we have here an artist-friendly, fast and scalable real-time approximation of light transport in translucent homogeneous media. Our technique allows developers to improve game visuals by simulating translucency with reasonable and scalable impact on the runtime. And, providing, especially now, where cost for development of video games is getting higher and higher, providing convincing results through simple means is essential in the development of high-quality AAA games. And we, Mark and I, but also other people at EA, hope that this technique will inspire developers in the continuous effort to improve games by promoting, the development of new techniques, that blend art, technology, and where convincing results don't always mean, exact math. So this technique is also published in GPU Pro 2, which is released this week at GDC, so you should definitely check it out. And I was wondering if you guys had questions. These are the previous Battlefield 3 and Frostbite 2 talks that we presented. They will be available on publications.dice.se in the following weeks. And Mark and I would like to thank the following people for for their time, multiple reviews, and never-ending support. So if you have any questions, I'll be gladly answering them. Thank you. I'm sorry? All right, so the question is, how do you combine this with real-time radiosity? So all the lights, let me go back actually. All the lights that you can see in this scene, too fast. All the lights that you can see in this scene are actually integrated with our real-time radiosity engine, which is powered by Enlighten. A light in this scene, generates radiosity, and it just blends well together. No, the bounce light doesn't propagate through the surface. Again, we're trying to keep things like super simple, so yeah, I understand. Cool. Thank you.
Yeah. Hi. I'm over here, so I just grabbed the microphone.
Okay, cool.
Elvis Presley style. So, neat trick, by the way. Thanks. Since you seem to be relying on ambient occlusion term, why don't you just calculate the screen space ambient occlusion and just use that? Why do you prefer to recalculate it for every model and then stream a bunch of textures?
Right. Well, the main reason behind this is that we don't want to have some, our GPU is already super busy, and I see what you mean, where you can actually do this in real time, like flip your objects normals, flip the polys. And
actually, I was thinking that you guys already have an ambient occlusion pass, so
right.
That's kind of, I don't know if that's true. So do you
have
a screen space ambient occlusion pass?
Right, we do. But
so
the thing
it's kind of for free for you, right? So, I mean, you don't have to give this special ambient occlusion, screen space ambient occlusion pass. You already have it.
Right, but the thing is,
it comes for free.
The thing is, we flip the normals. And because this is rendered from the inside of the object, you would have to render your objects twice and flip. You know what I mean?
Yeah, but you already have the normals in the G buffer.
Yes, we do. Yeah, but they're not. Yeah, okay, fine. We could flip them
in the shader.
Yeah. Yeah.
Okay, maybe something worth trying.
Yeah, we could try it, but you know what? In the case where you have really complex objects, we want artists to, and real-time AO is never like super smooth gradients and everything, and it doesn't take the full shape into account. It's only what you see, right? So that's why I'm having a bit of trouble here. But in the case where it's only what you see, there's some parts of the objects that are behind that, or that might be, that you don't see, that could have an influence on that map. And that's one of the reasons why we do it offline. But I guess it could work for some cases in real time, yeah.
That's a pretty awesome trick you got there.
Thank you.
So how did you, I think I might just missed this, so it's a silly question, but how did you get the material ID when you're storing the translucency inside of the G buffer? For the translucency color for inside of the G buffer?
Well, so we have a material ID for, we have several of them. The last one is the translucency one.
Yeah.
Okay, and so basically, if you look up that channel in the G buffer and the value is, let's say the last one you have is 4. So if the value you have in that channel is 7, well, obviously you know that it's translucency plus the rest is the texture. So I don't know if this answers your question, but this is how basically we filter and say, oh, this is translucency. So compute the
Oh, okay, gotcha.
And it's done in the light pass. So
right.
All right.
Thank you.
Yeah, we just shuffled things around a bit. But the thing is, the GPU Pro 2 article was, I had to submit that like 3 or 4 months ago, so we had time to fiddle things around. Yeah, this is the up-to-date latest. So we have different images and some different explanations in the GPU Pro 2 article, but you should definitely check it out. It's a good reference. Thank you.